Okay. Chapter 12 is, so chapter 12 and chapter 13 are about spectroscopy technique. What are spectroscopy techniques? Those are the techniques that light somehow at different wavelength is involved in the in this measurement or the technique. We have 4 different common spectroscopy that are used. One is IR, one is UV. We have mass spec, and NMR. With all of them, some sort of light is being used. Depends on how much light is consumed and what type of energy is being, the sample is being exposed. The response of the compound with that type of light or the type of energy is detected, how the compound responds, and that detection is going to be recorded. So detector detects the compound's response, recorder would record it, and then you would have like a spectrum. Spectrum, it's like, is a graphic, is data or graphical data that needs to be interpreted later. And if you, what you are learning, which is the introduction to spectroscopy, it's not is not the actual spectroscopy course. I remember for my graduate school, I took like between, I think, 6 to 8 different courses that only taught mass spectroscopy. And it was like the major concern was the mass spectroscopy. So with like 1 day or 2 of the class in organic 2 chemistry, we are not going to learn, but we at least want to make sure that is introduced. The IR spectroscopy is going to determine the functional group. That's the major application. You can also do, like, based on comparison of known to unknown samples, you can do identification of the compound, but mainly you determining the functional group. Mass spectroscopy, it determines the molar mass of the molecule, as well as the fragmentation. And what is the fragmentation? Like if you cut the molecule in pieces, is going to determine the mass for each fragment or each piece, which helps us to determine a structure formula for an organic molecule. Nuclear magnetic resonance, or NMR, would analyze the hydrogen environment, or the environment of the hydrogens in a compound. If the molecule has like how many CH3 groups, how many CH2 groups, or the hydrogen arrangement, basically, how it is, and it is very detailed, very helpful in order to determine a structure formula for a compound. The UV spectroscopy, we talked about the UV spectroscopy in last chapter. It can help you to determine if, for example, if you have a diene, is that diene conjugated or isolated? It can help you to determine like how many pi bonds your molecule contains if you do have like the molecular formula for the compound. So you can get pieces of the information. When you are dealing with the spectroscopy technique, not one single technique is not sufficient to determine the structure, but you basically get pieces of information from each type of spectroscopy. You put them together, the pieces of puzzle, and then you determine the structure of the of that organic molecule or organic compound. So when we talk about the region of the light, we want to learn about the light. We just basic definitions, not more than what you learned in general chemistry. Just to know that the higher the wavelength is going to be lower the frequency. Frequency is directly related to the energy. So the higher the frequency, the higher the energy is going to be, because we have the Planck's constant. And the wavelength is inversely proportional to the frequency. The higher the wavelength, the smaller the frequency. So if you're talking about low energy means that low frequency is low, or the wavelength is longer. If you're talking about high energy wavelength, that means it's short wavelength, or is high frequency. So some of the examples which you need to know the pattern. You don't have to memorize exact numbers, but at least you need to know that gamma rays has the highest energy and the radio waves has the lowest energy. You listen to radio all day, nothing will happen. But if you're exposed to X-ray for a long time, it's going to damage your cells. Gamma ray, even for a short period of time, it's penetrating, and it is very dangerous to be exposed to because of the high energy that is going to penetrate through the cells and is not safe for body. So we have the different approximate wavelength. So IR wavelength is between visible and the microwave. And if you are using IR, or basically you're using light in the IR region, the amount of energy that you can use, or it can be used for the compound, it's enough to vibrate the bonds. It's not enough to break the bond. It's just enough to vibrate the bond. So if you look at this diagram here, it shows the effect of the light in the IR region on the bond. It will stretch and then it goes back to equilibrium. So if it can be compressed and then or stretched, but this is the equilibrium. So when it's at the equilibrium, when it's stretched, when you add the light, the bond length is going to change. So the distance between the two nucleus is going to change. That's the D, or the distance between the two nucleus. And if there is a dipole moment, if there is a change in electronegativity, then the value of the dipole moment is going to change. Dipole moment, mu equals D times delta. Mu is the or the value for the polarity of the molecule. Dipole moment is basically definition how polar the bond is. Now, the value for compound A, or I'm sorry, for the bond in the status of A, is going to be different from the same bond in the B status, because the value for D is changing. So what happens in the IR spectroscopy, when you give the light to the sample, the bond is going to be a stretch. And when the bond stretches, the mu is going to change. So you have if this is the mu1, then you do have a mu2, and it's going to be D2 delta, and this is a D1 delta. So the difference between these two is going to be the mu1 and mu2 is going to be detected by detector, and it's going to be recorded. Also, the machine is going to detect how much light, or at what frequency or what wavelength the light was required to stretch this bond. The stronger the bond is going to require a stronger or higher energy light. So basically, the light at different region, or the light with different wave number or different frequency, is needed to stretch different bonds. And what we are going to do in this chapter, basically to look at some patterns, how the amount of the light that is needed is going to be different from one bond to another bond. What are some of the factors that is going to affect that? For a stronger bond, higher energy is needed. So if we are dealing with this table, if you understand this table, you understand the whole IR spectroscopy basically, but it does involve some memorization and just these, factors that is going to affect. How does carbon-carbon single bond is different from double bond from the triple bond? Which one is stronger? You might use the chat or the mic. You just answer which one is the stronger bond. The double bond is stronger than the single bond, and triple bond is going to be stronger than both of them. Okay, so if you want to stretch this triple bond, to stretch it, you are going to use, need, or this bond needs higher frequency. Okay, higher frequency or wave number. That means like how many wave per in each centimeter. So the higher this number, that means you have higher frequency, and higher frequency means higher energy. So for triple bond, you need 2200. The scale that we are dealing with, the IR region, it goes from 400 to 4000 per centimeter. The higher the number, the higher the energy of the light is going to be in that region. For CC double bond, around 1600. For CC single bond, it's 1200. So the stronger the bond, higher energy is needed. Let's say you have an unknown compound and you test it with the machine, you run it, you do the IR, try to get the IR spectrum for the machine, and you find a spectrum, and then you find a peak at 2200. What does that mean? That IR spectrum of a compound shows a peak at 2200. What does it mean? IR spectrum of unknown compound shows a peak at 2200. There is a triple bond. Very good. So that means there is a triple bond there. So if you're not dealing for that compound, and you are dealing with the compound that has a peak at 1700 and using this table, what does that mean? If you have a IR spectrum of unknown compound and there is a sharp and a strong peak at 1700, what does that mean? Your compound contains a what type of bond? 1700. Your compound contains a carbonyl group. Very good. So that's basically what you're trying to learn in this chapter. What peak, or peak at what location, corresponds to which type of functional group. So if you have a CO single bond, you would have a peak at 1100. If you have a CO double bond, the spectrum would show a peak at 1700. If you have a carbon-carbon triple bond, is going to show at 2200. And if you have a single bond, it would show at 1200. So basically, that's what we are learning. As the frequency is increasing, that means more energy is needed. If more energy is needed, that means that the bond is stronger. And if the bond is stronger, that means you have like a specific type of bond that is associated with each of these numbers, that they are very common. So basically, you need to learn about the functional group. Each functional group is going to show at what location. And since there aren't many of them, basically you have to memorize it. Some of the factors that is going to affect. Let's say we have peak at 1700 for okay, we have a peak at 1700, and we know that there is a CO double bond. Now, is this CO double bond is coming from ketone? Is that CO double bond is coming from ester? Is that CO double bond attached to a benzene ring? How are all these different from each other? That's another thing you have to learn, that if it says 1700 is not a fixed number, is not a written on stone number, it can change based on the chemical environment. Like for this ketone, if it's 1700, it's fine. And then what happens if it's conjugated? Your CO double bond is conjugated or is attached to benzene ring, that number is going to decrease to 1680. And again, it's not a fixed number, but it's going to be less than 1700. If it's attached to highly electronegative element like this, ester functional group, in the ester functional group, this is going to change to 1735. So your 1700 is not going to always stay at 1700. Two factors affecting. Conjugation would lower the frequency. That works for every spectroscopy technique. Electron withdrawing group is going to increase that number. So if you're like in the lab, if you're changing carboxylic acid, let's say you have a carboxylic acid, and then you are going to mix that with alcohol, and you want to change that to ester, carboxylic acid plus alcohol, that gives you ester. The CO for carboxylic acid would show a peak at 1715, but for ester, it would be at 1735 to 1745. So if you take the IR spectrum of the reactant, and it shows at 1715, between 1700 and 1715, but on product, it shows that this CO double bond is between 1730 to 1740, that confirms the product of ester has formed. So there would be a shift of the CO double bond. So there are applications to this in the lab for monitoring reactions as well. So we can look at the chemical environment of any of these compounds and say any of these functional groups, and say it may not be exact number that we see here. It could be lower. Like CC double bond for butene is going to be, let's say if that is at 1660, but in a benzene ring, it's that CC double bond, because it's conjugated with something else, that CC double bond is not 1660, and that could be at 1600, okay, for the CC double bond. So conjugation lowers that number, electron withdrawing group would increase the number. I kind of talked a lot about it, and is basically, I just want to make sure that you know what you are going to learn and what you are trying to learn in this chapter. So what I said is included in the next slides, but I kind of summarize it. So we have the fingerprint region. So I said, for simplicity, I use 400 to 4,000, and I say like 1,400, and then some books they cut off is a 1,600, and then they use from 1,600 or less than 1,600 as a fingerprint, and greater than the 1,600 to 4,000, they use it as the general region, which is like a common vibration happens there. Fingerprint area, more complex vibration happens in the fingerprint region. We try not to use the fingerprint region unless that's the only source of information that we have in this class. Okay, we try to stay in the general region, but if we let's say we have a CO single bond that shows peak at 1100, then we have to go into the fingerprint region. So just based on definition, between 400 to 1,400, that would be the fingerprint, and 1,400 to 4,000, that would be general region for the IR. So what is measured by IR machine is the change in dipole moment. As I said, the value for mu is changing because we are changing the length. The D is changing, and since the D is changing, as a result, the mu is changing, dipole moment is changing. Detector in the IR machine measures that change in dipole moment. So the major part of the machine includes sample holder. So we do have a sample holder. We have a light source. So sample would be exposed to light, or light would be shined to the sample. Then the detector is going to detect the response of the sample to the light. Then you do have a recorder. So these are the four major parts of the machine, or a spectroscopy technique. You have the light source, you have sample holder, you have detector, and you have recorder. The mechanism, it could be different from one machine to another machine. So the way that IR, or most IR are designed, they divide the light into two halves. One part of the light would go through the sample. The other half of the light would go through, like, as a reference. So then it's compared. The two of them are compared. And it's going to say, okay, the reference light was going straight, but the light that went through the sample had dropped in this area, dropped in this area, dropped in here, dropped in here. And then the recorder is going to record that, and it will give you the IR spectrum. So it's comparing the two pieces of the light, one going straight without going through the sample as a reference, and the other one is going through the sample. So four major parts again: light source, sample holder, detector, and recorder. The FTIR, meaning that the difference between IR and FTIR, meaning that this is going to scan more than one time and takes the average. So it's more advanced compared to IR machine. And I don't think any university is using IR. When I was using the IR machine in 1992, the machine that I used, it was a FTIR. So I don't think anybody is using IR. That means that it scans multiple times and take the average of the peaks, and then what is recorded is the average. So it's kind of normalized, or is optimized before it would be recorded. Okay, so we talked about the single bond, double bond, triple bond, and now the hydrogens that are attached to those. Like if you have a hydrogen that is attached to a sp3 hybrid carbon, this is going to show a peak at between less than 3,000, between 2,900 to 3,000. If you have a hydrogen that is attached to sp2 hybrid or carbon-carbon double bond, basically is a vinylic hydrogen, is going to show between 3,000 to 3,100. And if you have a hydrogen that is attached to sp hybrid carbon, is going to show a short peak at 3,300. So these are important. Hydrogens attached to single bond, hydrogen attached to double bond, hydrogen attached to triple bond. So you would see that. And also it says for the isolated versus conjugated and the aromatic, basically saying the more conjugation, the lower the frequency is going to be for carbon-carbon double bond. Any questions? Questions? Okay. If you don't have questions, we are looking at the sample IR spectrum. For the sample IR spectrum that we have, if I look at only the region that is like a general region after the 1400 here, if I look at these, we have peaks that are less than 3000. We don't have anything over 3000. If we don't have anything over 3000, that means there is no hydrogen attached to sp2 carbon. We don't have any peak at around 1600. Okay, if there is no peak at 1600, no peak here, that means there is no CC double bond. So this must be a saturated hydrocarbon like alkane. For alkane, the types of bonds that we expect or we have for alkane is a CH bond and a CC bond. Okay. So the CH bond, because the hybridization of the carbon is sp3, is going to be less than 3000, and that's what we see here. And then we have the CC bond that it's not very active here. It doesn't show, the peak is very short here. It doesn't show because when you have very like non-polar bond, if it's non-polar, that would be IR inactive. Because when we talk about mu, we have to have the distance, which there's always distance between two nucleuses, and difference in electronegativity or delta. If the value for delta for a alkane that is completely nonpolar is 0, it doesn't matter how much you stretch. The value for mu is not going to change, and since it's not going to change, then we are going to have very weak peak, or we don't see that. Okay. But if we have a CC double bond, okay, like here we have for the next one, we have a CC double bond. We see a strong peak at around 1600, and we know that is the CC double bond stretch. And we have peaks for CH. One type of CH is coming from sp3CH, and that would be anything less than 3000, between 3000 and 2800. That would be sp3. And if we have between 3000 and 3100, this is the sp2CH. So this basically is the CH hydrogen attached to sp2 carbon. So just get kind of used to this. The CH also shows peak around 1400. We had here for 1400. This is the bending. It's not a stretch. So is a CH bending, is not the CH stretch. The CH that shows a stretch here, that stretch is like a stretch like this, but this bending of the CH is like going in and out, like it's bending, going in and out. It's like scissoring. You have the scissoring, you have bending, and those peaks, they show less than 1600. But for alkane and hydrocarbons, it's kind of important because you don't have a lot of other peaks to depend on. So you just have to say, okay, I have a CC double bond here. I know that this is attached to CC double bond, that hydrogen, and these CHs are attached, these hydrogens are attached to sp3 hybrid. So when you are looking at the IR, you are not expected to learn about every single peak that you have there, because it's impossible. Sometimes these are not even real peak. These are just noise, background noise, like background noise here. So you are expected to learn about major functional group for this course, okay? So we are looking for major functional groups. What do you see here is hydrogen attached to CC triple bond. So if you remember from before, that should appear at around the 3300, right? 3300. And then the CC triple bond appears at 2200. So you look at the spectrum, you have a CH at around 3300. So we know that is coming from sp hybrid, and we have a So basically, if the formula is given, you break down what are the major parts of this formula. I know I have a SP CH. I have a CH that is the sp3. I have CC single bond. I have CC triple bond. These are the major part of this, or major functional group, or major bonds for this molecule. And that's what you see on the spectrum. The sp3 would show up here. SP would show up between 3000, or SP would show up around 3300. And then CC triple bond would show, CC triple bond would show around 2200. And then the CC single bond is going to be around 1200. Okay, so basically depends on how complex your molecule is and how many different type of functional group you have. You would see different peaks at different region. And if you know the location or expected location for each of these, you can interpret basically the IR spectrum. I talked about the IR active and IR inactive. Like this is like a perfectly symmetrical bond here. CC triple bond is expected to be at 2200, but when you look at the 2200, there is no peak. Basically, it says that because this is like perfectly symmetrical, it doesn't even show. And since is internal alkyne, there is no hydrogen attached to it, so no H attached to no SPH, sp hybrid H, there is no peak here either. So you do have alkyne, but there is no hydrogen that is attached to sp because it's internal alkyne. And because it's internal alkyne and perfectly symmetrical, it doesn't show any peak for CC triple bond. This is known as IR inactive bonds. But the CH stretches coming from sp3 is showing less than 3000. Questions? If you have questions, please ask now. It's better to ask your questions. Slow me down so you can, if I'm too fast, you have to tell me. It would be too late if I find out after the chapter is over, okay? So other peaks for IR or other functional group, let's say NH and OH bonds. OH would have a peak at 3300. NH would be 3300. So if you have a peak at 3300, how do you know is the OH or NH? The shape of the peak is important also, location and the shape. Sometimes the shape of the peak is going to help us to specify what type of functional group you have in the molecule. If the peak is at 3300 with the round tip, that is OH. For NH is going to be round, but one spike, okay? But if you have NH2, is going to be round with two spikes. Then we know that is a NH2. So you have two hydrogens here, but it shows as a spike. But if it's round, it's going to be OH. So shape is going to affect. So for alcohol, you would see this. Carboxylic acid also has OH, but for carboxylic acid, the OH for carboxylic acid is going to be very broad. It's going to start from 2500 and it would stop at 3500. So if it's very broad, that means it's coming from carboxylic acid and is not coming from alcohol. And also the other indication is that if you're dealing with carboxylic acid, you have OH, you also have a CO double bond. So you would have this peak plus a peak at 1700, and that is approximately 1700, okay? So you have two peaks, one for OH, one for CO double bond. What functional group do you have based on the molecule, the molecular formula? What do you expect here? You do have an NH, right? You have a CH, and the CH is a sp3. I don't see any sp2 or sp. I have NH. NH around 3300 with one spike is not round. And also the CHs are less than 3000. And these are the CH bending, CH2 bending, okay? For ketones and aldehydes, for ketone, CO double bond, around 1700, 1715, you have a peak at a strong peak because it's a very polar bond. The more polar the bond is, the sharp and strong it's going to be. If you see like a broad peak like that for OH, is because of the hydrogen bonding. Hydrogen bonding makes the peak in IR spectrum broad. Same thing for NMR. So if you have an NH and OH, because of hydrogen bonding, the shape of the peak is going to be broad. But when you have like a CO double bond, that is a polar bond, you would get like a sharp and a strong peak. It's kind of reaching the base of the spectrum. Short peaks like the like a CC triple bond, we had like a short peak right here around 2200 because it's not polar. And you have too many CHs. So you see this bond is kind of like stretched and is wider because of the number of the CH that you have. It can affect also the shape. Aldehydes. How aldehydes are different from the ketones. For ketone, you only have one peak that is for CO double bond. That's for ketone, around 1710. And for aldehyde, if you, this hydrogen is going to show a peak at 2700 and 2800, plus the 1700 that you have for the CO double bond. So for aldehyde, you get like 3 of them in a row. So you have, if you have all 3 of them, it shows that it's aldehyde, not a ketone. For carboxylic acid, I said already, you do have a peak for CO double bond, and you have a broad peak from 25 to 35 for OH. Here is a white peak for the OH from carboxylic acid. Goes from 2500 to 3500. And these spikes are not like the NH, because the NH spikes would be around 3300 here, okay? This spikes basically is the CH overlapping with the OH. If you didn't have the OH, okay, if you did not have the OH, the CHs would be here still, okay? The OH that is here is overlapping with the CH, and you see these spikes. CO double bond, strong peak for carboxylic acids. If you have 2700 peak and the 2800 peak and 1700, so all 3 of them is aldehyde. Now it's, you know, you see the concept is very easy, very simple. The only challenge is to recognize them, to be able to see that is if it's conjugated, if it's isolated, and also memorize some numbers. CO double bond when it's conjugated is going to be less than 1700. So one conjugation bond will conjugated with 1 pi bond, conjugated with benzene ring, it would be even lower. So it would decrease the frequency. CO double bond for amide is the lowest. So this is kind of exception, is the lowest, is going to show between 1600 to 1630 to 1660. That if you see it that low, that means you have amide. Of course, you have, when you have amide, you would have a peak at 3300 also, because it's the NH bond. The reason this is very low is because it's forming resonance. So you get this resonance forming. the two resonances that you have for the amide functional group. So basically your CO double bond is between CO double bond and CO single bond. CO single bond is at 1100, CO double bond is at 1700. So this effect of resonance is going to lower the CO double bond the greatest, more than conjugation, because it's resonance, it's not conjugation. So a 1640, that's a very low number for CO double bond, but it's explained by the presence of the pair of unshared electron you have for nitrogen. Questions? We talked about esters, and then for the esters, this value is between 1730 to 1740. So we know that is not ketone, is not aldehyde, is a higher number. So it must be either ester, or it could be like a anhydride. A cyclic ketone also is a high number. So you have to kind of pay attention. Now, since it's like each one individually is simple and easy to remember, but when you have to compare one to the other and the other choices, then you have to be, you have to think like very but like you have to put your investigator hat on and say, okay, how do I know that's the CO double bond? Is this 1785 is coming from a cyclic ketone, or is it coming from like carboxylic acid or anhydride? So look for other peaks around it. So if it's an ester, you don't have only the CO double bond, you also have a CO single bond. So you would see a very strong peak between 1000 and 1200. So that strong peak is coming from CO single bond as well. And just know that the cyclic ketone would show a higher number for CO double bond. The CN single bond, double bond, and triple bond, CN triple bond, they follow the same pattern as the CC single bond, CC double bond, and CC triple bond. Basically, it shows in the same region. The CN is more polar than CC, so the height of the peak is different. So if you had this short peak here, that could be like CC triple bond. For this long and sharp and strong peak is CN triple bond. A general pattern for location of different functional group in IR spectrum is given here. Like if you have the OH and NH, both of them appear in the same region, you must look for the shape of the peak. The CH, if it's less than 3000, if it's greater than 3000, or if it's at 3300, then you can say the hybridization of the carbon is different. Questions? There are tables and many tables that you can use them, but this is like a general table. It's showing again the approximate location for lots of functional group. Where would you find them? So what do you see from this spectrum? What can you see from a spectrum without reading the solution part? So you want to look over like the 1600, right? See what you have a peak that's 17. This is like around 1710, 1715. Okay, so we know that we have a CO double bond. That's very obvious. CO double bond, it could be ketone, it could be aldehyde, it could be carboxylic acid. Is this a carboxylic acid? Is the CO coming from carboxylic acid? A spectrum can be given to you and 4 different possible structure. Then you pick one as that. And or a compound can be given to you. One single compound could be given to you with 4 different spectrum. Or sometimes we get like a 4 spectrum with 3 compounds, and then you would have to match which 3 are the compounds. So it's not carboxylic acid, right? Why is not carboxylic acid? Because I don't see a broad peak here. So it's not carboxylic acid. But I see peaks that are at the 2700 and 2800, and then I have the CO. Most likely this compound is aldehyde. So you're looking for the presence or absence of evidence for one type of functional group. If you do have if you do a chemical reaction and you have the spectrum of the reactant, you have the spectrum of final product, that would make it much easier for you to determine if the reaction went through, because you already on the paper, you know what is expected, what type of product is expected to form. And then on the product spectrum, you're looking for those new functional group. Did it form or didn't form? Sometimes you're given a compound, unknown compound, and you find the spectrum, then you would expect that be a spectrum for compound A, but still is similar to compound B. So is your compound A or compound B? What you can do, take compound A and compound B, take a spectrum of the both of known sample and compare to your unknown. Whichever is the closest match, it would be the name for your compound. So based on comparison, that would be the strongest case. Okay, the application for IR spectroscopy. One of the major application is to determine functional group, basically identifying your compound, trying to get stuck closer to what type of compound you're dealing with to identify your compound. Monitoring chemical reaction. So when you are monitoring chemical reaction, basically what you do, as I said, you get the IR spectrum for reactant, you get IR spectrum for product, and compare. Or on the paper, since you have the chemical reaction, you have the reactant and product, you expect what peaks should be on the reactant spectrum, IR spectrum, what peaks should be on the product, and you look for those peaks. If there is for example, if you're going from you're doing reduction experiment. Let's say you're doing reduction experiment and you want to go from ketone to, then I'm just going to make it simple. Let's say you have this and you want to go to a product of OH. What do you expect? For the reactant, you have peak at 1700. For the product, you have a peak at 3300. That's the point of difference. So that's what you're looking for. Everything else is kind of similar, and that's where it's going to stay as a similar peaks. It will stay. But you are looking for the point of difference. Let's say on the product, because this is experimental value, and you did actually prepare this compound in the lab as a result of reduction of the ketone. You take the spectrum, IR spectrum for the product, and you see 33 peak at 3300. You also see a peak at 1700. What does it mean? You didn't expect to have this peak at 1700, but it shows there is a peak at 1700. What does it mean? Any response? It means that, is anyone typing? Should I give time? It means that your compound is not pure. It has alcohol functional and it has like ketone functional group. That means your compound, it has some leftover of the ketone. So the reaction was not complete. Sometimes your reaction is not complete, or other times when you prepare a compound in the lab, you have to take other steps and you purify your sample. If your sample is not purified properly, then you get peaks that are not expected to be there. So you just have to be able to recognize, understand what's going on. And if you see, if you spectrum for alcohol that shows a peak at 1700, you have to take back that alcohol. You have to do recrystallization. You have to purify it, make sure that you separate the ketone from the alcohol, and then bring and do IR spectrum again. IR spectroscopy has also been used for quantitative analysis. Basically, they measure the area under the peak, and then they can say, what's the concentration? One of the machines that was using this technique is the intoxilizer. Intoxilizer is a machine that is used in the, for law enforcement, is used to determine the breath alcohol concentration. And the suspect would blow into the machine, and then they get the IR spectrum. When they get IR spectrum, because the alcohol has the OH bond, it can show a peak. The area under the peak is calculated, and the machine is designed to automatically translate that to the blood alcohol concentration, and reports that what is the blood alcohol concentration. And in Florida, if it's like 0.08 or lower is allowed, and anything higher would be not allowed. And that unit, I think, is a gram per deciliter of the blood. So the peak area is the area under the peak also has been used in the machine for intoxilizer. The handheld devices that they are using for roadside detection also, it does work based on the IR spectroscopy. Questions? No questions about the IR? Okay. For the mass spectroscopy, which is the last part of the chapter 12, basically you have a machine. It has 4 components. You have your light source, you have your sample, you have your detector, you have your recorder. You bring in the sample, you shine the light or you give energy, and then the detector is going to detect what is happening or the response of the sample to the light or energy you are giving. Recorder would record, and what you need to do is to interpret that spectrum. So if you have the mass spectrum, the mass spectrum looks different than the IR spectrum. Mass spectrum, you would see lines like this, and it can go from 0 to a number. And what is showing here is basically mass or M/Z ratio. Basically, as you go from left to right, the number is increasing. And when you see mass of fragment, let's say at 15, if you see a mass, that's basically is a CH3 plus, is a methyl carbocation. So if you see peak at 29, that would be CH3, CH2 plus, and that is a ethyl carbocation. Then you could have like a 43, and that is like propyl carbocation. Then you would have like a 57 for butyl carbocation, and any combination. So if you have these peaks, and then last you would have like a peak. Last peak is called the mass spec, the molar mass. So molar mass of the compound is showing as the last peak, except for like one case when dehydration takes place for alcohol, that this is going to be like a molar mass minus 18. That's dehydration of the alcohol, results in the M minus 18. So you would have M minus 18 showing as the last peak. But that's not very popular, very common. And often last peak is the M plus or the molar mass. You also have a base peak. You see, like this is the base peak. Base peak is the highest peak or the most abundant peak. And that means the carbocation that formed to show that mass was the most stable one, or the most popular one, or the most stable one that can make to the detector. So how does the mass spectrum machine works? There are multiple different ionization technique, multiple different detection technique. And I said I've taken like so many courses, and that's not what we are going to cover here. We are just looking at like electron impact ionization. And the detection is based on like the time of flight, basically. Electron impact, that means that you have the filament that will generate electrons, and those electrons are going to hit the compound. This is your sample. And magically, one electron comes in, removes one electron from your molecule, and then it would change to like a cation. So it would generate a carbocation. Since one electron is removed, when you have one carbocation, the other side would change to free radical because it has an unpaired electron. Let me see if I have a diagram for the mass spec. No, but when you remove that electron, when one electron is removed, then the molecule is going to be cut to free radical. Oopsie. We change to free radical and carbocation. Now, what happens to the free radical? So let's say if you have your light source here, you have your light source here, you have your sample, and then you have your detector, and you have your recorder. The light source is going to hit the light. This is going to change to cations and other pieces, cations and free radical, cations and free radical. The detector only detects the carbocations. If there is any free radical, this whole system works under 10 to the minus 5, let's say, torr. And I hope you recognize what does it mean. This is like very high vacuum. So anything that is neutral, anything that doesn't have a plus charge, is going to be vacuumed out. It would be like there's a funnel that you would see like all free radicals and anything neutral coming out. Only the ones with the positive charge would make. Now, sometimes you have your molecular compound or the molecular ion making to detector. Other times there's fragmentation. So when you have this, it's going to break down to 2 pieces and you get like 2 pieces. One of these 2 pieces is going to make it to the detector, the one with the plus charge, and the other piece will be drained out. So you basically, what you do in mass spec, you are going to take the sample, change to ions, ionize your sample, and lead it to detector. Detector would detect the mass of the sample that is hitting the detector, and it would record the mass. If you give more energy, you break some of these bonds, and when the bonds are broken, you get fragments. So when you see this is actually a fragment of the ethane. So it's a methyl group, but it's a fragment of the ethane. It's not just a different compound. It came from after the carbon-carbon bond broke. So when you bring your sample and the electron beams are going to ionize that, it goes through detector. This is like a time of flight detector. That means the compounds that they have, the fragments that they have greater mass, they would travel shorter distance. The ones that they have a lower mass, they would travel longer distance. And based on the flight time or the distance traveled by each ion, detector is going to detect the mass of it, and then it will record the mass. The vacuum pump is going to remove anything that is not positively charged for this detector. Now, when you see a mass spectrum, as I said, the unit here is m/z, mass to charge ratio. Often we use, like for this course, we use a 1+ charge. So basically mass/z is basically showing the mass. It starts from 0. We don't have anything with the 0. So 0 mass. The lowest mass that we have is a H, and that's not going to make the detector. Basically CH3 for this, CH3 plus would be the smallest unit that you probably see, unless you're doing elemental analysis, then you would be, it would give you like 1. So it depends on the compound that you're dealing with. So the highest mass that is showing is the mass of the molecule or molecular ion. The one with the highest abundance, that would be, is known as a base peak. So know the definitions. What are other peaks? Other peaks are fragments. Let's say you have a cut through this methyl group. What is left here is 85, is 100 minus 15, and that is 85. So if this piece makes it to the detector, that's 85. If this piece, if it's cut through here, then this piece would make it, and you get like a 57. If this cut is through here, this part is going to make it to the detector, and that is a 43, and so on. So each one is the mass of fragments. The last one is the molecular ion, and the longest one is the base peak. Often mass spec is connected to like a different device, which is a separating or purification, separation. Like if you have GC mass spec, and what happens in GC, the compounds are going to go based on the retention time. They would leave the column one at a time. So basically you're not mixing compounds. The compound that is going to the mass spec is going to be pure sample. This is just allowing one sample at the time to come in. And if someone who's doing the research know already the compound or their interest because they did the GC before, it takes like 2 minutes from the time you inject it until it gets to the other part, is going to then at 2-minute time allow the sample to go into the mass spec. And then they know the compound of the interest is in the mass spec, which is going to be ionized first, and then would be mass filter. So based on different masses, it will reach to detector, and detector would detect and recorder. The point of this slide is show that the mass spec can be connected to GC, where GC would purify your sample, and it will send only pure sample. Because if your sample is not pure, it's like a garbage in, garbage out. If you put like impure sample even in the melting apparatus, you don't get the melting point that is going to help you to identify the compound. All you can say that your compound is not pure because it's going to have like broad melting range. So the more pure the sample is, the better the result is going to be. Mass spec can have like different sensitivity or accuracy, higher resolution. For high resolution mass spec, it can detect the mass of the elements up to like 4, 5, 6 different different decimal places. Exact mass is the question. So let's say if you find a mass that is 44, and do you know that 44 is coming from propane, or if it's coming from carbon dioxide, or if it's coming from other compounds that they have 44, so, or approximately 44. With the high resolution mass spec, the exact mass is measured, and when the exact mass is measured, then they can discriminate the mass of one compound against all others. So even the first decimal place is the same for these two, but the second decimal place is not the same. So you need at least 2 or 3 decimal places to distinguish between these two compounds. So that is used when you have like high resolution mass spec. Some atoms, they have different isotopes in nature, and the different isotope in nature, it can be also showing different mass in the mass spec. So if we have chlorine as a chlorine 35 and chlorine 37, so if you have a compound that would show a peak like this, and this is like a 3-to-1 ratio, 3-to-1 ratio, or 75-25 ratio. If you have this ratio of the peak height, and the difference between these two is like 2 units only, these are not coming from 2 different fragments. It's coming from the same fragment, but the first one contains chlorine 35, the second one contains chlorine 37. So the condition is that if you want to look at the isotope ratio, the difference between these two, it should match with the isotopic ratio. The height ratio, it should match the ratio of abundance of this chlorine 75-25. Now, what happens if you have very similar situation and you have this 50-50? You have difference of 2 here. Okay, you have the difference of the 2 here, but the height is the same. Which of these isotopic ratio would show the same height? Since it's the first time you're looking at this table, I would point out to it is bromine. Okay, it's like 50.5, and then you have like 49.5. So this is almost same height. So if it's different by 2 unit only, 2 unit mass only, it's not coming from separate fragment. This is isotope, is an isotopic ratio. And from the height ratio, you would recognize that this is coming from bromine, because the height ratio is determined based on the percent popularity or percent abundance for the M and M+2. So for bromine, we have bromine 79, we have bromine 81. Height ratio is 1-to-1 or 50-50. So if they are equal, that means it's not chlorine. Because for chlorine, you have a 75-25 ratio or 3-to-1 ratio, and the height ratio is going to be 3-to-1. So if you have a height ratio of 3-to-1, that means you have chlorine. If it's a 1-to-1 ratio, it's going to be bromine. And those are the most popular one for your class that you are going to be, kind of responsible. And then what do you see for iodine? Iodine has a 127. Okay. So if you see a mass difference of 127, like a huge gap between like first fragment, second fragment, you have like 127 exactly. And that 127, it means that you have a iodine. Okay? So a gap of 127, it's 90% of the time or 95% of the time is going to be iodine. So you don't see like a ratio, but you will see a huge gap between. Oxygen, you get like only like 2% of the isotope, but sulfur, you have like 4%. So don't worry about anything that is less than 4%. The ones that you are basically dealing with is the sulfur with the 4%. Then you have your chlorine 37, which is 25% to 75%, and bromine is 50-50. That's the isotopic ratio. So when you see these lines, these little lines, what does it mean? That's not chlorine or bromine. What is this small line? That is like carbon 13. So 1% of carbon in nature is carbon 13. Like 98.9% is carbon 12. So when you see the like this little marks here, that is coming from compound that contain or the carbon 13 contribution to the mass. In this case, even if you didn't have all these writings here, these units are separated by like by 2 only. So you have 122 and 124 mass, and you can estimate that by just dividing this distance between 120 and 130 by 10, and then look at these numbers. So if it's between 122 and 124, you only 2 units. This must come from isotopic ratio. The height ratio is almost the same, and the only one that has same height ratio is bromine. So we know this compound contains bromine. If the bromine leaves, what is left? Propyl group. What's the mass of propyl? That's 43. Bromine is a good leaving group, and if it leaves, it's going to create that carbocation here. So that's why CH3, I'm sorry, the propyl group is giving you the base peak also. So you also have like a 29 here. That could be ethyl. And then you have some 15 here, very little 15, and that could be the cleavage of the first carbon-carbon. So you have cleavage of the first carbon, and then you have the cleavage for the second carbon, and you have cleavage for the third carbon. These are all possibilities. You're not dealing with one molecule only. You have Avogadro's number of the molecules in 1 mole. We are not injecting 1 mole, but even if you do like 0.05 or 0.002 moles of the sample, you still have a lot of these compound that is going to molecules that is going through the ionization. And this could happen at for different molecule, but they're all possibility. If A happens, if the cleavage of A happens, you would see this for A. If B happens, you would see this for B, because you have the 29 that is going in. And then if C happens, you would see the 43, and then you would see this as the molecular ion. Okay, why we don't have a peak at 79 or 81, or is very, very low? Because Br, when it leaves, has negative charge. And we said that only ions with positive charge will make the detector, not the ones with the negative charge. So you don't see a large peak of the 79. But if it shows as a molecular ion, yes, it will show as the molecular ion. It's intact with the molecule, but it's not going to show as standing alone Br minus, because Br minus doesn't get to the detector, only the one with the plus charge. And the reason for that is that in order to take those ions into detector, they put negative sign, negative charge or negative plate next to detector to kind of attract those positively charged. So if it's negative, it's going to run the opposite way. It's not going to make it to detector. And we are only in this book or this chapter, we are only talking about the, ions with the positive charge making to the detector. Now, if you change your detector, then it's possible to make it like negatively charged. But this detector covered in this book, course is just a positively charged ion. And based on the time of flight, you recognize, or detector recognizes the mass of each fragment. Okay, the height ratio 3:1, most likely you have chlorine. The 43 base peak. Yes, when chlorine leaves, you end up with isopropyl, and that is a base peak that is showing here. For sulfur, you would see like a 4% only, so it's very small isotopic ratio for the molecular formula. And then when you have the cleavage of the methyl group, you have your base peak there. You could have cleavage on both sides, so you do have like the 29 as well. For compound A and compound B, what do you expect? At least tell me if you have a chlorine or bromine for compound A, based on the isotopic ratio. Compound A contains chlorine or bromine?
Bromine.
Bromine, because you have a 1-to-1 ratio. From compound B, what do you expect to have? Like a huge gap between the 29 and then 156. That gap of 127, that would indicate that compound B contains iodine, right? Okay, compound C, chlorine, bromine, or iodine? Compound C, chlorine, bromine, or iodine? And now C. How would you find out if it's chlorine, bromine, or iodine? You look at the ratio, height ratio here, 1, 2, 3. That's 1. It's a 3-to-1 ratio, and that shows that you have chlorine. And when chlorine leaves, you have like 55. That's the molecule or molar mass minus the 35 you have. So when the ionization takes place, you have your molecular ion or radical cation molecule, which is the molecular ion. This can make it to detector. It can also break in pieces to 2 pieces. One is carbocation, one is free radical. Is not going to be observed because it doesn't have the plus charge and only the fragment with the plus charge. The more stable carbocation, the faster it's going to form, and higher population of that is going to reach the detector. So if you have fragmentation that you cleave off the 29 here, ethyl group, you would get a fragment that could be, either side can take the plus charge. If one side takes the plus charge, the other side would take the free radical. So always one takes the plus charge. So every time you have a fragmentation. So even if you have fragmentation here, this side can take the plus charge, this side take the left side can take the plus charge, right side would take the free radical, or vice versa. So if there is a cleavage at the red color we have here, you could have cations of 57 and you would have a cation of 29. Both of them would reach the detector. Now, the other pieces, of course, is going to be vacuum out of the system. If you have a cleavage between carbon number 3 and 4, Of course, you would have 43 that is going to make to the detector. So you could have a plus charge on this side or to the right side. So every one of them can make to the detector. Let's say if the cleavage is at 71, you would see a peak at 71. And I said that there's a possibility of 15 also, but you don't see the 15. 15 is like very low concentration here. The reason for that is because this is not stable. So if it's not stable, it's not going to make it to detector. We have so many other pieces that they are more stable than the methyl group, but we still know that we do have a CH3 attached to this molecule because we could observe M minus 15. That means that methyl group was cleaved off. So molecular mass, the base peak, and isotope ratio. Remember that for mass spec. And then the fragmentations. What gives the most, what gives the base peak is the most stable carbocation. Like in this case, why 71 is not the base peak? Because when 71 forms, this part is stable. This part is going to be stable, but the free radical that is forming here is not stable. And because the piece that is forming, that is like left out, is not stable, so is not very popular. It looks like molecules are more fair than people. They don't only think about their own, they think about the other piece also. Is not stable piece. The second piece is not stable. So that makes the 57 cut more popular, and you make the 57 cut is going to show as the base peak. Okay. For mass spectra of the alkane, you see like a M minus 15, you see M minus 29, M minus 43. Basically, the alkyl groups are kind of showing. So, and they are kind of separated by 14, like a CH2. The cleavage here, when you get for when you have like alkyl group attached to benzene ring, cleavage at the benzylic position is popular because what is left is going to be very stable because it's creating multiple resonances. So this would show whatever the mass is, it would show the base peak. So this fragment is favored fragment, a popular fragment. Allylic carbocation is going to be stable. So if you have cut at 55, that is going to give you allylic carbocation. It makes sense that that is going to happen because the plus charge here is allylic and is more stable, and that gives you the base peak. Like explanation, if you get a question, someone asks what type of question you would expect, like it would say like, what makes the fragment 55 to be base peak? How would you explain it? Because a cut at 55 or M minus 29 would give allylic carbocation, and that's the most stable carbocation from this molecule. Okay, it's 7:35 and you didn't remind me. Let me remind myself.